Take a look at the homework that we had last night, page 523, number 6 to 10. Any issues with any of those questions? 9. Going once, going twice, that's it. Okay, number 9 it is. Number 9 says, compare the distribution of charge on hanging aluminum and glass rods that both are touched at one end by a negatively charged ebonite rod. What's the difference between an aluminum and a glass rod? That's what we got to look at first here, right? Why would there be a difference in the distribution of charges? Well, because aluminum is something and glass is something else. They both have different characteristics. What is it that differentiates those two, Cam? What differentiates aluminum from glass? Right, aluminum is a conductor and glass is an insulator, right? Well, what's the difference between a conductor and an insulator? Why would there be a difference in a distribution of charges if we've got a conductor versus an insulator? What is a conductor? Yep. Yeah, a conductor will accept electrons or give away electrons more easily than an insulator, right? It's easier to transfer charges because those electrons aren't as tightly bound to the nucleus. All right, so we've got a hanging aluminum rod. Let's draw the aluminum right here. And then let's hang the glass right there. The aluminum, okay, is touched by a negatively charged ebonite rod. So ebonite is kind of a plasticky, rubbery material. The glass is also touched by the negative charges. Okay, they're both neutral to start off. What's going to happen to the aluminum? What's going to happen to the glass? Well, if you got aluminum, you're going to get a negatives probably going from this negatively charged ebonite rod to the aluminum, right? So that's going to try to balance them out. It's not necessarily going to be perfectly balanced because we don't have equal size, we don't have equal shape, and we've got two distinctly different materials. But the bottom line is they're both going to become negative, right? The aluminum will accept some of those negatives and become a negatively charged object. It's got protons in there as well, but it's got more electrons than protons. What's going to happen over here with the glass? You might get a few electrons moving over, but for the most part, it's not going to take negative charges from this ebonite rod. Right, it's going to remain, for the most part, neutral. So what's the difference in the distribution of charges look like? Well, the aluminum becomes negative, and the glass remains, for the most part, neutral. Okay. Let me give you an example here, guys, that you guys have all seen before, and some of you may have even thought of before. You touch, let's say, two conductors together. Let's say you touch a balloon to a conductor. Okay, we know what happens, right? Touch a negatively charged balloon to a conductor, that conductor becomes negatively charged. The charges balance out. What should happen at this point? After this charge transfer has taken place, what should happen? What should the interaction be between the aluminum and this negatively charged rod here? They should repel each other. So they're initially attracted. Negative is attracted to neutral. Then they touch each other. Charges transfer. And then all of a sudden they repel each other because we've got like charges, right? Why is it that when you rub a balloon against your hair, it becomes, say, negatively charged? Can't remember whether it's negative or positive, but let's say it becomes negatively charged. Then you put it against the wall, and it sticks to the wall. You ever notice that? Why doesn't the balloon transfer negative charges to the wall become negatively charged, and then the wall and the balloon repel each other? In other words, why does the balloon stick to the wall? Why doesn't it just fall down? Okay, yeah, that could be part of it. Yeah, that's part of it, because the wall is really big normally, okay, and the wall, even if it does take a lot of electrons, those electrons get spread out, and it's still effectively like the Earth, right? It's still essentially neutral and isn't really going to repel too much. Okay, what's the bigger thing, though? Yeah, neither the balloon nor the wall are good conductors, right? So the wall's not going to accept those electrons very easily. The wall remains basically neutral, okay? And of course, if the balloon is still negatively charged, the wall is still neutral, then what's going to happen? Okay, the balloon is still going to attract to the wall. So a negatively charged ebonite rod will be attracted to the aluminum, but then once it touches, it will repel. But a negatively charged balloon will be attracted to the wall. When it hits the wall, it's going to stay there because the wall is not a conductor versus the aluminum that is a conductor. Does that make sense? Good. 9b, After a small negatively, what's the distribution of charges after a small negatively charged metal sphere momentarily touches a larger neutral sphere? What's the distribution of charges going to look like? Well, they're both conductors here now, right? Is there going to be a transfer of charge? Yes. Which way is the charge going to go? From the negative metal sphere, the small negative sphere, to the big one, or the big neutral sphere to the small negative? Which way is the charge going to go? From the small negative to the big one, right? Not because it's small and large, but because it's going to go away from the negative toward the positive, right? Now, what's the distribution going to look like? Are they going to be equally charged? Are they going to be balanced out like, for the most part, we talked about they are? Probably not in this case. Okay, which one's probably going to end up with more charge? Probably the bigger one, because the bigger one's able to hold more charge, right? Make sense? We're good at that? All right. Today we're going to move forward and for the first time this unit do a little bit of mathematics, other than averaging numbers together, that is. Okay, we haven't done any mathematics in this unit at all. You know what that means. The homework starts up again here. Okay, we haven't had a whole lot of homework in this unit so far. We're going to start having a little bit more here. We're going to talk today about the Coulomb torsion balance experiment, which led us to a law called Coulomb's law. The Coulomb torsion balance experiment is real similar to an experiment performed by a guy named Cavendish that you learned about in Physics 20. It found for us the gravitational constant, big G. You remember the equation F is equal to gm1m2 over r squared? Newton's law of universal gravitation. Hey, big G, Newton never found. Big G was found by a guy named Cavendish with a torsion balance experiment. Okay, the law, Coulomb's law, which is a real similar to Newton's law of universal gravitation, was derived from a torsion balance experiment as well. This is what it looks like, more or less. This is a simplification of it, but it looks more or less like this. I'm going to make this a little bit smaller, actually. Start off on this side. Here's the top of a box, or the ceiling. Okay, hanging from that is a thin string or a thin wire. On the end of that thin string or wire is a little rod. We've got two objects, one on each end. They're equal mass so that this thing balances and doesn't tip over. The first one over here on the left-hand side, we're going to call Q1. That's charge 1. Q is a symbol, by the way, for charge. So that's going to be charge 1. The other one, I don't even care if it is charged. Okay, it doesn't have to be charged at all. Okay, we only need one of them charged. We just need both of those masses there so that the thing doesn't tip over. Now my fist is going to represent another charge, Q2. It may be the same charge. It may be opposite charge. Okay, I don't know whether Q1 is positive or negative. I don't know whether my fist is positive or negative. It doesn't really matter. When I bring my fist, this other charge Q2 nearby Q1, what's going to happen? You can see the shadow there, right? See the shadow. My fist Q1 or Q2 is coming near Q1. What's going to happen? It's either going to attract or repel. Right, Q1 is either going to move towards Q2 or it's going to move away from Q2. Now, that tells us whether it attracts or repels, whether they're like charges or opposite charges. That's not really overly relevant to the experiment that was performed here. What we care about is not so much what type of charge we have, but rather how much charge we have. Now, Coulomb wasn't able to determine exactly how much charge Q1 and Q2 had. But what he was able to do was determine the relative amount of charge. So in other words, he starts off with a certain amount of charge. We call it Q. He touches it against something that's neutral, and it becomes a half Q, right? Because they balance out. He touches that against something that's neutral, and it becomes a quarter Q. Touches that against something that's neutral, it becomes an eighth Q. So he was able to manipulate the value of Q1 without actually knowing what the value of Q1 was. He was able to cut it in half and cut it in half again, and so on and so on and so on. He was also able to do the same thing with Q2, manipulate the value of Q2 without knowing what it actually was. He was also able to determine the distance quite easily between Q1 and Q2. Right? Take a ruler, basically, and measure the distance between my fist, Q2, and this charge, Q1. So he knows Doesn't know the value of Q1, charge 1, but he knows the relative value, so close enough. He doesn't know the value of Q2, but he knows the relative value, close enough. He knows the value of a distance that separates them. We're going to call that R. Okay, the distance that separates them here. You can measure that easily. The only thing he needs now, and this is the tricky one, is the force of attraction or repulsion. You guys have all done this before, for sure, whether it was last week or whether it was 5 years ago. At some point, you've been sitting on a swing set at a playground, and you twist that swing set around, okay, and then you get it twisted as far as you possibly can get it twisted, and then you let it go and you spin around, right? Everybody's done that, right? You guys know when you do that, the more you twist it, the harder it is to twist it, right? The more force it requires to twist it. The torsional properties, or the twisting properties of that swing set, the chain on that swing set, dictate that more force is required to twist it more. Well, the same thing applies here. As this string right here is twisted more as a result of a bigger force of attraction or repulsion between Q1 and Q2, okay, we know there's going to be a bigger force. Coulomb could do experiments to determine how much force was required to twist it a certain amount. So now when he goes and does this experiment, if that string twists 3 degrees, well, he knows how much force was required to do that. If it twists 4.5 degrees, he knows how much force was required to do that. If it twists 8 degrees, he knows how much force was required to do that. So based on how much the string twists, or in other words, the torsional properties of the string, he's able to determine the value of the force of attraction or repulsion. Does that make sense? Bit of a simplification again here, but it works for us, okay, what the level of detail that we need to know. So he knows Q1, he knows Q2, he knows R, he knows F. Now what he's going to do is actually set up the experiment. In fact, 3 different experiments. In the first experiment, he's going to have, of course, 1 manipulated variable, 1 responding variable, and then some control variables. The manipulated variable in the first experiment might be Q1. He changes the value of charge 1. Okay, maybe it's Q, and then it becomes a half Q, and then it becomes a quarter Q, and an 8th Q, and a 16th Q, and so on. He doesn't know what it is in coulombs, but he knows what it is relative to what it started off as. The responding variable would be the force of attraction or repulsion. And again, he's able to measure both of these. The control variables, I just did a science fair project, helped my son and Mr. Kruger's son. They were partners in a science fair project. And we talked about variables and manipulated and responding and control variables. Okay, the control variables, even in grade 5, when we talked about it a little bit, they recognized that the control variables have to be everything else. Everything else has to stay the same. Okay, if we're changing Q1 and F responds to that, then what has to stay the same here? Okay, so let's keep R and let's keep Q2 the same. Okay, we bring Q2 nearby Q1. All right, measure the force. Bring it nearby Q1 again, but change the value of Q1. Measure the force. Bring it nearby again, change the value of Q1 again. Measure the value of the force. When Coulomb does this experiment, gets some data for it, ends up plotting a graph, always responding versus manipulated, right? F versus Q1. The shape of that graph ends up being a straight line. Okay, that provides him with a good relationship between F and Q1. We'll talk about that relationship in just a second. The second experiment that he would have done would have been to manipulate the value of Q2. So now we're keeping Q1 the same, we're changing the value of Q2. What responds to that? What changes because we change the value of charge 2? Going to be the force again. It's always going to be the force that's the responding variable. But what stays the same here? What can't change in the second experiment if we're trying to see the effect of Q2 on F? Okay? I'm sorry? Let's not say radius. It's the distance that separates them, but r. Yeah, okay, you're right. And Q1. Q1's got to stay the same now, right? Plots a graph of F versus Q2. And the shape of the graph ends up being exactly the same. It's a linear relationship. Finally, he does his third and final experiment. This time he manipulates what? What's he going to change this time, do you think? The distance that separates them. So he's keeping Q1 and Q2 the same this time. This time he's going to change with every trial how far apart Q1 and Q2 are. So he's going to manipulate R. The responding variable will be the force, of course. And the control variables will be Q1 and Q2. He's got to keep the charges the same now. Plots a graph of F versus R. When he does that, he gets a little bit of a crazy relationship. The first two relationships tell us that as Q goes up, Q1 or Q2 goes up, F goes up. In other words, F is directly related, the magnitude of F is directly related to Q1, and the magnitude of F is directly related to Q2. In other words, as both of those charges go up, F goes up as well. In the bottom one, as R goes up, what happens to F? It goes down. That's not a linear relationship at all. In fact, it's not even an inverse relationship. It turns out to be an inverse square relationship here. As R goes up, F goes down really quickly. As R goes up, F goes down quicker than R goes up because it's an inverse square relationship. So what does Coulomb do with this? He puts it all together into a law. He says, look, I know that F is related directly to Q1, and it's related directly to Q2, and it's related to the inverse of the square of R. Let's put that together in a law that we call Coulomb's law. F is related to Q1 times Q2 over R squared, or in other words, F is equal to, have you guys done proportionalities in math class? If something is proportional to something else? F is proportional to Q1, Q2 over R squared. In other words, it's equal to something times that. What's that something? It's a constant. We're going to call that constant Coulombs constant. And the value of Coulomb's constant is 6.67 times 10 to the 11 Newton meter squared per coulombs squared. Kind of a strange set of units, but you don't need to worry about remembering those because they're always on your data sheet, right? That constant is on your data sheet, as are the units. Just for reference here, we'll remind you what Q1 and Q2 is. They're the charges, charge 1 and charge 2 in coulombs, and R would be the distance that separates the charges. And that unit is going to be, that distance is going to be measured in meters. Does this law look at all familiar to you? H question? Yes, it is. What have I just done? That's the gravitational constant, right? Actually, it wasn't even the gravitational constant, but it was really close. The gravitational constant is 6.67 times 10 to the minus 11. I had 10 to the positive 11. 8.99 times 10 to the positive 9, thank you. Does this remind you of something? Paige just kind of gave you a hint, a real big hint to the answer to this question. Does the structure of this equation remind you of anything that you did in Physics 20? The gravitational equation, right? The gravitational force between two masses was Gm1 m2 over r squared. The electric force between two charges is Kq1 q2 over r squared. Q being the charges instead of the masses, obviously. Yep. Say it again. What do you mean, can I break it up? So we'll answer that in a few days when we get to that gravitational field stuff. All right. So the two equations look the same, right? A couple differences. Okay, namely the biggest difference, of course, is that we're dealing with charges instead of masses. We're also dealing with a different constant. Big G, the gravitational constant found by by Cavendish, 6.67 times 10 to the minus 11 Newton meter squared per kilograms squared. That's a big difference, right? That number is quite a bit different. Finally, the last difference would be that, of course, gravity has to be an attractive force, right? The electric force can be attractive or it can be repulsive. Does that make sense? Which force do you think is usually a bigger force? Not attraction or repulsion, because that can be, depends on whether they're negative or positive charges. But which force do you think is going to be a bigger force, Cam? Up here. Gravity or the electrostatic force? Why do you think electrostatic force will normally be a bigger force? Yeah, the constant is astronomical compared to the constant of gravity, right? 10 to the positive 9, 10 to the minus 11. The constant is 10 to the 20 times bigger. So all other things being equal, the electric force will be a stronger force. In the grand scheme of things, guys, there's 4 fundamental forces. We're not going to talk about them all today, but essentially gravity is one and the electromagnetic force is another force. Gravity, in the grand scheme of things, is an incredibly weak force. An incredibly weak force. Okay, we think of it as being a big force, right? Because we're attracted towards the Earth. But the only reason that we feel that force of attraction towards the Earth is because the Earth has a mass of 10 to the 24 kilograms. The Earth is massive. What force of gravity do you feel between you and the person next to you? Nothing, right? Because gravity is a weak force. Okay, if you were charged, okay, you take a balloon, okay, put it near your hair. What happens to your hair? Makes your hair kind of stand up on end a little bit, right? The electrostatic force is way stronger than gravity. You take a balloon, is your hair affected by the gravity caused by the balloon? You're not even close. Is it affected by the charges on the balloon? Yeah. Okay, you see your hair kind of moving around all staticky because of that electrostatic force. Okay, an electrostatic force is normally, all other things being equal, way bigger than a gravitational force. We just think of gravity as being big because we're used to dealing with it in such a big scale. Could electricity be used to give a force similar to gravity? Yes, in the sense of an attractive force that could keep things in orbit, say, around something else. Sure. Gravity keeps the Earth in orbit around the sun. Okay, electrostatic force keeps the electron in orbit around the nucleus. Okay. Well, they're both pretty big forces then, right? Well, the reason that gravity is able to keep the Earth in orbit around the sun is because the Earth is really heavy. Okay, 10 to the 24 kilograms, and the sun is even heavier. It's about 100,000 times heavier. So you've got two literally astronomical masses, and that's why that's a big force, right? Okay. It doesn't take very much force at all to keep an electron in orbit around the nucleus, but the electrostatic force supplies it easily to keep it going around the nucleus, right? Next. Yeah. Here's just a little summary that compares the two forces together, Coulomb's law and then Newton's law of universal gravitation. They're both what we call inverse square relationships. In other words, F, whether we're talking about Coulomb's law, we're talking about gravity, F is inversely related to the square of the distance. In other words, a graph of F versus R would look like this. The magnitude of the force, well, which one's bigger? Well, Coulomb's law, the electric force, is a big force because the constant is 10 to the positive 9. Newton's gravitation is a small force, a really small force. Constant is 10 to the minus 11. Take a step back from this for a second and think like, well, why is it that way? I mean, it's amazing when you think about it how the universe wouldn't even exist if these constants were slightly different. Imagine if the force of gravity was even 10 to the minus 10 instead of 10 to the minus 11. Imagine if the force of gravity was 10 times stronger than it is. Nothing as we know it would even exist. Okay, the universe wouldn't have ever formed the way it has. Okay, life wouldn't exist. So these are two dramatically different numbers. It's a good thing they're two dramatically different numbers because we wouldn't be here to learn about it if they weren't. What about the direction of the forces? Well, Coulomb's law can be attractive or repulsive versus gravity, which is strictly an attractive force. Okay, let's take a look at a pretty straightforward example here, 530, question number 10.1. There's a small metal sphere with a negative charge of 2.1 times 10 to the negative 6 coulombs is brought near an identical sphere with a positive charge so that the distance is 3.30 centimeters. What's the magnitude and the type of the force of one acting on the other? Okay, there's a couple things that I want to point out here strategically with these questions before we actually do the question. The first thing is, okay, when I see the word negative charge, I'm probably going to want to circle that in red, just like I did when in my momentum unit when I saw the word south, or I saw the units kilometers per hour. Okay, I'm probably going to want to circle that it's a negative charge to remind me that one is negative, one is positive. Now, the other thing they're going to want to circle here is the centimeters because I don't want to be in centimeters, I want to be in meters, right? Okay, standard units, meters. Now, I also have to write down my givens. Okay, this would be one charge, this would be another. Which one's Q1 and which one's Q2? Doesn't matter, does it? Right? Q1 times Q2, Q2 times Q1, doesn't really matter. Let's call this Q1, let's call this Q2. This is going to be R, the distance that separates them. And we're looking for the magnitude and the direction of the force. Now, of course, the equation that we're going to use here, pretty straightforward, KQ1, Q2 over R squared. The value of K is on your data sheet. Okay, on the left-hand side of your data sheet, if you don't remember what it is, 8.99 times 10 to the 9. Q1, watch what I'm doing here. Q2 over R, we're going to make that 0.0330 meters, and don't forget to square that. What does it look like I've forgotten here? The negative for the charge, right? But I haven't forgotten it. Okay, even though that's a negative charge, I don't ever want to plug the sign of a charge into an equation, ever. Okay, for us, negative in an equation is going to mean direction. This negative doesn't mean direction. This is a type of charge. Now, it's important in determining whether it's attractive or repulsive force, but it's not important mathematically. Don't ever put a negative sign into an equation for charge. Okay, again, for us, negative in an equation will always mean a negative direction, not a negative type of charge. Let's get the value of that force now. You get 24.76 newtons, which we're going to round to 24.8 newtons. Thank you. Now, is it attractive or repulsive? The equation doesn't tell us. If you take a look at the equation over here on the left-hand side, the force has absolute value signs around it. That means that the equation will never tell us the direction. It's only ever going to give us the magnitude. It's a vector, but it's only going to give us the magnitude. Right, Paige? So how are we going to get the direction? Yeah, sorry. From the negative. We got a positive sphere, we got a negative sphere. Is it going to be attractive or repulsive? Attractive because opposite charges attract. And we're going to spot that, right? Because we circled the negative to remind us that one of them's a negative. Well, if it was repulsive, then you'd have two positives or you'd have two negatives, right? Yep. Yeah. Like charges are going to repel, opposite charges, unlike charges are going to attract. Make sense? That's a pretty straightforward question, right? Just a couple little things though, right? Make sure you pay attention to those units because you're often going to see centimeters there. Okay, make sure you pay attention to whether it's positive or negative charges. It's not going to matter for the math, but it is going to matter for the final part of the question. Is it attractive or repulsive? Don't forget to square the R. There's a really common mistake, by the way, guys. Forgetting to square the R. I guarantee if this is a multiple choice question and you forget to square R, I guarantee you that one's there. That's an option. And lots of you are probably going to pick it. Let's see what we can do with this question real quickly here at 5:30, okay? All right, we have no issues with this question. Let's take a look at one more example problem, and then we'll wrap it up for the day here. This one says the two spheres in 10.1 are momentarily brought together, and they touch each other, and then return to their original separation distance. What's the force now exerted by one on the other? Does it change? We get the same two objects, right? Is the force between them going to change? It is. Can anybody tell me why it's going to change? They touch together, and what happens when they touch together? They try to balance out, right? So let's assume that they do balance out. Whenever you get a question where they touch together, and right, we have to assume that they do balance out. They started off as, what do we have? Negative 2.1 and positive 1.5. When they touch together, what do the charges become? These were the old charges. Q1 now becomes what? What would it be? Negative 0.3 or negative 3.0 times 10 to the minus 7? Q2 will also be negative 3.0 times 10 to the minus 7 coulombs. Now the question is just as easy as it was before, right? The distance that separates them, 3.30 centimeters. Or 0.0330 meters. Notice we're dropping the sign of the charge again. Okay, it's negative on both of them, but we're dropping it when we plug it into the equation. Tanner, what do we get there? 0.74. Anybody else get that? 0.743 newtons. Is that going to be attractive or repulsive? It's going to be a repulsive force because they're both like charges now, both negative charges. Does that make sense, guys? The force becomes so dramatically different even though we have the same objects because those two objects have different charges now. We've touched them together, they've balanced out, the charges are the same. Okay, the force becomes 0.743 newtons. Right? All right, here's your homework for tonight. You get the practice problems on page 531, and I think there's only one of them actually on page 531, I think. In addition, I want you to do worksheet number 6, please. Worksheet number 6, which is on all of this stuff as well. So practice problems, page 531, and worksheet number 6, please. And that's it for today. Have a good night, guys.